So hello, this is Richard Chen and come from Delta Electronics, Taiwan. And I am Renjun would like to take this opportunity to introduce our high power open rack design. So Delta have development open rack series product, like including the power supply, PDU, power shift.
One quick
PDU.
Sorry to interrupt you, Richard. Are you sharing a screen?
Yes.
Try. I'm not seeing it.
Okay. 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 So Delta have developed a series of open rack products, including the power supply, PDU, power shift, PDU rack, and the rack manager. And start from 2012, we developed V1 open rack, and it helps us to understand the data center IT rack design concept. And also after that, we gathered some of the customer as us to do some leverage from the open rack to design the IT rack for them, like we do for the Scorpio, we put a firmware on it, and also try to increase the V1 open rack power to 28 kilowatt. Around 2014, then we do the V2 rack design, and also we have some assurance kit for customer. For example, security kit door, or to enhancement the earthquake design, we do the seismic kit, and it's around 2017, then we do the 48-volt V2 rack design. And currently, we are doing the V3 open rack design. We think the open rack V3 just the beginning for late generation. So we are thinking about what's the next possible extension solution in the future. So we checked recently the rack inquiry from our customers, start from 4 years ago, 2016. I think most of the requirement is belong to the 10 to 20 kilowatt. And 2018, then we find 75% customer looking for the rack power is around 30 kilowatt. And however, this year we're looking at a lot of customer come to us ask to design the power higher than 50 kilowatt. So it encourages us to start thinking how to design a high power rack design. So to achieve this high power open rack, so we can based on the power density and the maintenance to select the suitable power architecture. And also think about how to do the power distribution and bus bar design. And also cover the power module and the shape design. And also study how to do the rack power input. And since this is the high power rack, so the cooling solution is also very important. So later on, I will share of this kind of the study. So when we're talking about architecture, there are two kinds of the power architecture solution in the IT rack. The first one is we take the PDU, connect with the data center AC power source, and use the AC power core to distribution the power to the each server. And the other one is similar with OCP, we use the power shift. So same connect with the AC power for the power shift, and power shift connect with the bus bar, and bus bar provide a 12 volt or 48 volt bus, and server can use clip to connect with them. So from these two kind of architecture, I think for the rack type PDU solution, majorly is we put the PDU and they use the AC power core to distribute the power to the each server. But when you go to the power shift solution, I think the bus bar, no matter 48 volt or 12 volt, is what we use to distribute the power to each server. And for the check these two kind of the configuration, we can focus on some of the key factors. First one is we need to pay attention on the cable arrangement for the PDU type. And for the power shift type, we just need to put the power shift installation in the stable location and use the scoop or clip to connect with the bus bar. If we consider the 100 kilowatt, so that we need to have a 3 PDU for power distribution to consider the this PDU spacing and the cable arrangement spacing. So we put some of the reference number here for the spacing. And after that, we check the power shift. According to the recently industrial technology, for the power density check, probably we need to have the 4 OU to fulfill the 100 kilowatt power shift. So compared to these two solutions, we find the power shift, power density getting higher is our candidate to do the design for the high power rack. And then we can check the bus bar design for the V2 12 volt and the V3 48 volt. We check the bus bar probably can handle the 500 amp. So if we consider the 100 kilowatt and utilize 12.5 volt, and total output current is 8,000 amp, is 6 times 500 amp. I think it's not easy to handle that. But if we want to implement the 100 kilowatt for the 48 volt bus bar, only the output current is around 2,000 amp. It's 4 times of 500 amp. So I think the V3 48 volt bus bar can handle it. So let's make an example of that here. For example, we have a 500 amp bus bar and the voltage is 48 volt. So that means if we put up 2 power zone, each power zone can handle is around 25 kilowatt. So totally is 50 kilowatt. But however, if we put the power shift in the central location in the zone 1 and zone 2, I think zone 1 they can handle the current. Right now it becomes the 500 amp plus 500 amp is around 1,000 amp. So each power zone can handle the 50 kilowatt. So zone 1 and zone 2 they can handle around the 100 kilowatt for them. So I think that means we can have the complex size 48 volt power, 50 kilowatt power shift, and put 2 power shift in the V3 open rack. Then we can build a 100 kilowatt open rack. So the next step is to do the power module design. So in this high power range, since the input current and output current is big, so probably most of the people will want to discuss, can we do the single phase or 3-phase power module design? And then there are some of the findings that we would like to share with you. So you can see here is the single phase topology 1. This is normally what we're doing for the power shift design. We will use the 3 pieces, 6 pieces, or 12 pieces. The number is around multiple pies of 3. Then we do this kind of design. Then when we do the 3-phase rectifier design, we can base on the power demand to select the suitable number for the rectifier. It's not need to become a 3 times number for that. So it's also good for the increase the power density. One of the benefit we can have is if we use this kind of a 3-phase design, we don't have the neutral connection. So we can save some of the infrastructure cable and the switchgear cost. But if we want to do the similar thing in the single phase, then that is easy to achieve it. The other thing is we consider the phase balance because when we do the single phase topology, phase balance, we need to utilize the single phase power supply output current sharing. Then that will impact the input current sharing. If in some of the load condition, the current sharing is not good, so the phase balance will not also good. Also, we need to consider abnormal condition. If some of the power module fail, it also will impact the single phase topology current sharing. However, if we do the 3-phase design, that means the 3-phase already controlled in this 3-phase rectifier, so it's now so have this power balance concern. Another is one of the interesting topic we learned from our customer is if the current sharing did not well in the single phase approach, and then I mean in the neutral wire with some current. In some of the worst case, if the neutral winding impedance is so big, that may impact the power system stability. But however, if we do the 3-phase design, since we don't have the neutral winding, so we need to consider this kind of the unbalance and cause the power stability issue happen. So furthermore, we make a table to compare with these two kind of the solution. To check the power balance and the input THD, we think the 3-phase can get some good result. And since we have less pass count for the 3-phase, and I think the power density for the 3-phase and pass count are better than the single phase. I think only thing about the control of free set is complicated. But however, we have some of the UPS and heavy DC power design. So three-phase right now, the topology is very familiar with our team. So, and also for the industry. So we can leverage some of them to do the three-phase design. So according to pre-page analyze, so we find a three-phase rectifier is more flexible. So we determine to develop a three-phase product for next generation data center application. So here is the address spec for that. It's input voltage range, 370 volt to 530 volt, 6 kilowatt for the power module, and output voltage is 54 volt, but it's adjustable from the 42 to 58 volt. And the efficiency and THD, you put a very high target here, and this is a dimension here. So based on this design, we can achieve higher than 50 watt per cubic inch design for the power density. And then we can have a brief introduction for this three-phase rectifier. What we want to use is the Vienna three-phase PFC. It utilizes the three-phase bidirectional switch, and it also is the three-level topology. And input only the face-to-face connection, no neutral winding. And also we can utilize the 600 volt semiconductor device. And since the output have a two-stage for 400 volt, so we can use the DCT connector with them to provide the output voltage. And the Vienna rectifier can decouple into 3 single phase. So the traditional single phase PFC control, we can leverage from them. This is a product we want to use, including the input fuse, EMI filter, and the three-phase PFC. And here we're 400 volt bus here, then connect with the DC-DC, then we output voltage 50 volt. And primary and secondary, we use the DSP to control that. So here is some test result we can share with you. This is our EBT sample test. I think from the THD input THD testing, even the high 9 and the 480 volt and the 380 volt, we can meet our requirement, our target. But for the efficiency, we have the 0.3 to 0.5% we need to overcome. So there are something we still under debug. And later on, we are discussion about how to do the power shape design. So this is an example for the single phase. In the single phase design, normally we're doing this way. We put a number 1 and number 4 power supply connect with 9-1 and neutral. Number 2 and number 5 power supply connect with 9-2 and neutral. Number 3 and number 6 connect with 9-3 and neutral. So when we do the change the power supply to 3-phase, so we remove the neutral wire first and connect with 3-phase input. Since the it is a 3-phase, so current will be a little bit smaller, so we can use a small wire for that and connect the output together. And then we can not. And also, we don't need to have 3 times of number for this power supply. So we can reduce some number for the power supply. And also, since we have a reserve some of spacing for the power supply spacing, so we can enlarge the power supply output power. So this is a power shift we do for the 50 kilowatt. Actually, we can up to the 54 kilowatt. Same with the 48 volt output. And also, we have the standby 12 volt is provide the power to the measurement. Then we use a CAN bus for internal communication. So to check the real side and the front side for this design, we reserve space for 10 pieces power supply, and also the spacing for red monitor device. And you can see the first layer, the input of first layer will connect with the AC input 1, and the second layer, the input of second layer will connect with the AC input 2. And similar with open rack V3, we use the 40 volt bus power clip to connect with the bus bar. And we keep some RJ45 here is we can have the CAN bus interface and current sharing signal that can utilize the multi power shift in parallel operation. So for the input of the power, first thing is we need to select a suitable input plug. So we find the IEC 60309. They have some 63 amp, 2 kind of lamp. So one is belong to the 380 to 450 volt input. The other one is the 480 volt input. We can utilize these 2 power core as an input. And then similar with the V3 power shift, we just use the pluggable OCP type of connection, connect with the power shift. You can see each power shift can have 2 cable flap. So for the whole rack, they have 4 input cable connect with the input. And the other approach is we can design a 2U PDU. This PDU have 2 input and 4 output. And this 4 output is connected with the power shelf. And you can see from the rack, real side, we have 4 cable connected with this power shelf. And from the input side, we just use like the power data center input cable direct connect with the input terminal block. And this input block can be a single 1 or 2. Then we can do some of custom design modify for that. It's not so complicated. And following, I will arrange to introduce some of the cooling solution for this high power rack.
Good afternoon. Then I will present a cooling solution. We propose a cooling solution for 100 kilowatt per rack system. The cooling system is hybrid, including liquid cooling and air cooling. The major heat, such as from CPU or GPU, is dissipated through the core plate and then to the cooling tower. The other minor heat, maybe 20% to 30%, is dissipated by rear door heat exchanger and through the chiller. So this is better for PUE performance. There are 2 coolant loops for the rack. One is 45 degrees C for CPU cooling. The other is around 14 degrees C to rear door heat exchanger and to cool down the air temperature from rack. In traditional air-cooled heat sinker, it is very difficult to have lower than 0.1 degrees C per watt thermal resistance. However, for corporate cooling, 0.05 degrees C per watt is a typical performance. This can easy to solve over 300 watt CPU heat. The cooling system in rack is with a pair of manifolds and a liquid to air heat exchanger in rear door. The rear door heat exchanger we propose is 30 kilowatt and 50 kilowatt. This depends on how much heat dissipated from air-cooled components. For manifold design, it is with hot swap primary connector for server online installation and maintenance. The manifold is also with guide pin for connect mating. For infrastructure level cooling, we have the CDU and the manifold to provide the cold water to the rack. The manifold includes the rack type and the underfloor type. The CDU capacity is 1.2 megawatt for corporate cooling and 600 kilowatt for rear door heat exchanger cooling. The system is with water leakage sensor. If sensor detects the water leakage in one of the rack, the signal will back to the controller in manifold. The controller will shut off the water to the rack. This can prevent the water leakage to damage the whole system.
So Delta, we did do lots of the data center solution, including the open rack, including some of cooling and also for the UPS and some of the infrastructure solution. And if you are interested in our solution and product, please feel free to contact directly with us. We are happy to share our experience and the learning from the OCP with the members. Thank you everyone for the time today. This is the end of our presentation. Thank you.
Thank you, Richard and Delta team. Great presentation. I'm glad to see a lot of progress here. I'm going to see if there, I saw a couple of questions from Bill. He's asking, does Delta also have 48-volt inverter solution?
Yes, we did have some 48-volt inverter. Right now, we are using data in the telecom application and also work for the other data center customer for this kind of the edge computer application. So that means they utilize the
48 volt inverter.
Is it clear now?
Is it 48 volt inverter?
Yeah, the input is 48 volt. The output
Okay.
is 330 volt AC. Yes.
Okay.
Yeah. And the inverter can do the in parallel function. So we can extend in the power.
All right. I see a couple of slide question asking about the slides or the presentations. They are going to be posted in later on that you can go ahead and download the presentations or watch the videos later.
Okay.
Looks like there was one more question also from Raul, maybe. How do you manage that amperage on the bus bars? There's probably, I think maybe about halfway through the presentation probably is what he's referring to.
So currently the bus bar what we use is still reference on the V3 open rack. So if some of the customer worry about the bus bar temperature, we can put some thermal sensor for the bus bar and connect with the power shelf. Then power shelf also will provide this kind of information to the rack management. So we also have some design example for the bus bar temperature measurement.
One more question. So
Yeah.
does this rack comes with a BBU?
Right now, it also have some. It depends on customer, so we can also put the, for example, put a V3 BBU in this rack. But we need to check the spacing for that, because the 100 kilowatt probably he will utilize a lot of spacing.
Yeah, that was I was guessing. So
yeah.
If there is no BBU possibly in the rack, why are you going to use the wide range 48 volt? Why don't you use the fixed, like the narrow range 48 volt concept?
Right now, actually, because our power module design, the output voltage cannot be adjusted. Default is fixed 54 volt. And if the customer want to adjust the output voltage, it can be through the rack management to adjust the output voltage. And if you want to have some battery charging function, then we just modify our control circuit so it still can implement that.
Okay, so it allows the voltage to change and works for different applications.
Yes.
And even for the narrow range concept with the 50 volt fix, it can work. I understand.
Yeah.
Okay. Thank you so much. I think we are out of time. Is that correct, Caleb?
Yeah. There was one more. I'll just ask the question here, and maybe you can, Richard, you can respond through the FNTech virtual chat. It's how's the 200 amp brought in on the AC input? What size wires are being used? So we won't have time to answer it verbally here, but if you could, I'd appreciate it if you could go into the chat and answer that question, Richard.
Okay, no problem.
Thank you. Thank you.
Thank you.